Now we just see the lag compensator and whose transfer function and everything which we completed, right? Now we will see that compensator is a lag compensator or not, we will verify. Okay. Now how we can verify? So we will verify by using the transfer Bode plot. Now this is V naught of S by Vi of S, which is equal to 1 plus tau S by 1 plus alpha tau S. Now this is the corner frequency 1 by tau, and this is also the corner frequency 1 by alpha tau. This is the corner frequency 1 by tau, and this is the corner frequency 1 by alpha tau. Now see here. Now these are the corner frequencies. Now corner frequencies should be right in ascending order. First one is pole, next one is 0. Who is nearer to the origin? That is having highest time constant, least corner frequency. This is the least corner frequency. Who is away from the origin is having highest corner frequency, least time constant. Therefore, this is omega C2. So omega C1 belongs to pole, omega C2 belongs to 0. So magnitude plot. Magnitude in terms of dB, V naught of S by Vi of S. Magnitude in terms of dB versus frequency. This is the corner frequencies in the ascending order. First one is pole, next one is 0. This is omega C1. This is omega C2. Starting magnitude is 0 dB. Starting slope is 0 dB per decay. Starting magnitude is 0 dB. Starting slope is 0 dB per decay. Now this is up to the first corner frequency. Now the first corner frequency is one finite pole. One finite pole produces a slope of minus 20 dB. Now this is minus 20 dB per decay. This is up to the first corner frequency. The first corner, up to the second corner frequency. Omega C2 belongs to one finite 0. One finite 0 produces a slope of minus 20. Now this is one finite 0 produces a slope of plus 20. Plus 20 minus 20. Now it will become 0 dB per decay. Okay. Now this is 0 dB per decay. So this is Bode magnitude plot. But what we required to draw the Bode phase plot. So once if you draw the Bode magnitude plot, the phase plot diagram, which is very easy. Now what is the phase plot? Phase in terms of degrees. Phase angle. Phase angle in terms of degrees versus frequency. Now this is omega C1, this is omega C2. Now 0 dB per decay, which means 0 degrees, minus 20 dB per decay means minus 90 degrees, 0 dB per decay means 0 degrees. So this is phase is completely depends upon frequency. So if you see here, now this is approximated phase plot. So now this is which phase? Is a positive phase or a negative phase? This is the negative phase. Now this is the frequency at which the phase is changes, and this should be the maximum side on the negative values. Okay. So what is the frequency and what is this phase? Then I am already giving one shortcut method for that. Omega m is the geometrical progression of two corner frequencies, omega C1, omega C2. What is omega C1? Omega C1 is square root of 1 by alpha tau, omega C2 is 1 by tau, which is equal to 1 by tau into root alpha, because this is omega C1 1 by alpha tau, this is omega C2 1 by tau. Okay. Now what is the phase? Now the phase phi m, which is equal to sine inverse alpha is greater than 1 here, right? Alpha is greater than 1, therefore this is alpha minus 1 by alpha plus 1, where tau is R2C2, where alpha is R1 plus R2 by R2, where alpha is greater than 1. This is the magnitude plot and this is the phase plot. Phase in terms of degrees versus frequency. Clear or not? Okay. This is about a magnitude plot and this is the phase plot. Then this is a lagging phase. Therefore, this compensator is said to be a lag compensator. Now, whatever the circuit which we are finding, now this compensator is nothing but lag compensator. And I am already saying that this is the output, then this is the output, the same first order system, this is the output, you are taking across a capacitor, then it will act as a integrator, capacitor 1 by S integrator. Therefore, this is the gain versus frequency characteristics. This is gain versus frequency characteristics. This is the pass band multiplied with gain 1 and this is the stop band. This is the pass band multiplied with gain and this is the stop band. Therefore, the voltage across a capacitor, therefore 1 by S integrator. Therefore, this is the low pass filter and the lag compensator. The lag compensator will act as a low pass filter. The lag compensator will act as a low pass filter. This is the low pass filter characteristics. Okay, note down. Okay. So all are looking similar, but all are not same. All are differ. Okay, because here tau is there, different, and alpha is different. Values and ranges and everything will be differ. Now you just recollect what we are studied in the lead compensator, the same. Now effect of lag compensator. Effect of lag compensator. Now what is the effect? First one, lag compensator produces finite pole and finite zero. You know that. This is the lag compensator, First one is finite pole, next one is finite zero. Right? The lag compensator produces a finite pole and a finite zero in the left hand side of S plane. Lag compensator is a low pass filter, means low frequencies. Low pass filter means similar low frequencies, means bandwidth is less. When bandwidth is less, what happens? When bandwidth is decreases, rise time is increases. When bandwidth is decreases, rise time is increases. When rise time increases, what happens? You know that. When rise time increases, settling time is also increases. Therefore, system becomes, when bandwidth is decreases, rise time is increases. When rise time is increases, settling time is increases. Therefore, system becomes slower or sluggish. System becomes slower or sluggish. And now see here. Now this is the lag compensator is similar to PI controller. I means integral. Here is also low pass filter, integrator, integral controller. Why PI controller means? The PI controller will produce one pole at origin. Now here is also the first one is pole. Lag compensator is similar to PI controller. Next, lag compensator bandwidth is decreases, therefore noise power is directly proportional to bandwidth. Therefore, noise power is decreases. Bandwidth is decreases, noise power is decreases. When noise power is decreases, signal to noise ratio, then this noise power is decreases, therefore signal to noise ratio is very high. When the signal to noise ratio is very high, such that effect of noise is very less. Effect of noise is very less. That is the reason why, therefore, lag compensators are preferable over lead compensators. Lag compensators are preferable over lead compensators. Not only that, because lag compensator will not create any attenuation like lead compensator. So, cost and complexity is less compared with lead compensator. This is the reason why we prefer lag compensators over lead compensators. Okay. Now, these are the effect of lag compensator is produces a finite pole and a finite zero, and lag compensator means low frequency, low pass filter, and bandwidth is decreases, rise time is decreases, settling time is bandwidth is decreases means rise time increases, settling time increases, system becomes slower, sluggish. Okay, and this is PI control because this is integral, and bandwidth is decreases, noise power is decreases, signal to noise ratio is very high. This is the reason why the lags are preferred over leads. Okay, note down. Clear or not? Okay. Now this is the effect of lag compensator. Okay. Now you see here, this is the lead network, and this is the lag network. This is the lead network and this is the lag network. Then if you cascade each other, now if you cascade each other, this combination is nothing but lead lag compensator. Okay, this is the lead network, lag network, and this combination is nothing but a lead lag compensator. Now what is the circuit? You know the lead network. This is the lead network. This is the lag network. Now this is the lead network, this is the lag network. Now the combination of this lead lag compensator, now this is nothing but a lead lag compensator, means it produces both leading phase and lagging phase, then that compensator is said to be the lead lag compensator. Okay, but there is no need to worry about the lead lag compensator, because you know the complete characteristics of the lead network and you know the complete characteristics of the lag network. Then you just club those two characteristics, then it will automatically get the lead lag compensator. Now see here. Now I'll write here. Now what is the first network? The first network is lead network. Lead network will produce a finite zero and a finite pole. Finite zero and a finite pole. Now this is the lead network. Now whose time constant is R1 C1 alpha, which is equal to R2 by R1 plus R2, where alpha is less than 1. What is the next network? Next network is lag network. Lag network will produce finite pole and finite zero. Minus 1 by alpha tau, minus 1 by tau. This is the lag network. Now where tau is R2 C2, where alpha is R1 plus R2 by R2, where alpha is greater than 1. Now this is the pole zero sequence of lead lag compensator. What is the pole zero sequence of lead lag compensator? 0, pole, pole, 0. A number of times this question is asked in different competitive examination. What is the pole zero sequence of lead compensator? What is the pole zero sequence of lag compensator? What is the pole zero sequence of lead lag compensator? What is the pole zero sequence of lag lead compensator? Like that the question. 0, 0, pole, pole, pole 0, 0, pole, 0, pole, pole 0. Like that the options are available. Okay. So if you know the lead network, lag network exactly, then you can easily find any combination. Okay. So this is the pole zero sequence of lead lag compensator. Now here itself I will just form a few objective questions here. Which network is nearer to the origin? Students, tell me which network is nearer to the origin. Then the lead network which is nearer to the origin, which network is nearer to the origin, that network is having highest time constant. Very good. This is the lead network which is having highest time constant. The lag network which is away from the origin, therefore which is having lowest time constant. This is highest time constant. This is the lowest time constant. When the time constant is more, frequency is less. When the time constant is more, frequency is less. The lead network will occur at lead. The phase lead will occur at low frequencies. The phase lag will occur at high frequencies. Noda? The phase lead will occur at low frequencies. Phase lag will occur at high frequencies. Okay, this is will occur at low frequency. This will occur at high frequencies. Now the time constant of lead is greater than the time constant of lag. The phase lead will occur at low frequencies. Phase lag will occur at high frequencies. Both will occur at different frequencies. And not only that, then also you just see here. This is gain versus frequency characteristics. What is the first network? The first network is lead network. Students, one shortcut method I am saying, you just remember this. Lead, L-E-A-D. How many letters are there totally? 1, 2, 3, 4. Now, lag, how many letters are there here? Totally 1, 2, 3. This is one shortcut method for easy to analyze. More number of terms, high letters. Therefore, this is high pass filter. Less number of letters, low number of letters. Therefore, this is low pass filter. You can remember like this. High number, more number, high pass. Less number, right? Low number, low pass filter. Okay. Now, what is the first network? Lead. What is the lead network? Lead network will act as a low pass filter. This is the low pass filter from 0 to this particular frequency. This is the lead network. Okay. Oh, sorry. What is the lead network? The lead network will act as a high pass filter. High pass filter means this particular frequency is to high frequency. All the frequencies follows greater than this. This is the high pass filter because the first network is lead network. Now what is the next network? The second network is lag network. Lag network will act as a low pass filter. Low pass filter means from 0 to this particular frequency. Now this is lag network. The lag network will act as a low pass filter. So now the combination of the lag lead compensator, see here, now this is the combination of a lead lag compensator will act as a which filter? Band pass filter. Therefore, here is also you can easily identify. This is the frequency axis. Now the lead will occur at low frequencies. Lag will occur at high frequencies. Both will occur at different frequencies. Lead will occur at low frequencies. Lag will occur at high frequencies. Both will occur at different frequencies. Therefore, the lead lag compensator will act as a the lead lag compensator will act as a band pass filter. If it is a band pass filter, the pole 0 sequence in S plane is 0, pole, pole, 0. This is the pole 0 sequence of band pass filter pole 0 sequence. Okay, note down this. Okay, now this is the lag network, this is the lead network. Now this combination will act as a lag lead compensator. So this is the lag network and this is the lead network. So this combination will act as a lag lead compensator. Okay, now we'll see. Now, what is the first network? The first network is lag network, right? The first network is lag network. Therefore, the lag network will produce a finite zero and a finite pole. The lag network will produce a finite zero and a finite pole. This is the lag network, where time constant tau is R2, C2. Where compensator constant alpha is R1 plus R2 by R2, where alpha is greater than 1. Now what is the next network? Next network is a lead network. Lead network will produce the lead. The next network is the lead network. Lead network will produce. Now see here, this is the lag network. Now the lag network will produce first is finite pole and finite zero. Now this is the lag network. First it will produce a finite pole and next it is finite zero. Next network is a lead network. Lead network will produce a finite zero and a finite pole. So this is the pole zero sequence of lag lead compensator, pole 0 0 pole. Now this is the lag network, because lag network means alpha greater than 1, and this is nothing but lead network. This is the lead network where time constant is R1 C1, where alpha is R2 by R1 plus R2, where alpha is less than 1. Okay, note down. Now see here, which network is nearer to the origin? This is the lag network. This network is nearer to the origin. Therefore, lag network is having highest time constant. The lead network will have least time constant. Now this network is having highest time constant. Therefore, the lag network is having highest time constant because which is nearer to the origin, and lead network is away from the origin, is having the lowest time constant. Therefore, now the lag will occur at low frequencies, lead will occur at low frequencies, lead will occur at high frequencies, both will occur at different frequencies. And I am already giving one simple method. Now see here. Now what is the first network? Lag. Lag means less number of terms. Less number of terms means low frequencies. This is the lag network. The lag will act as a low pass filter. What is the next network? The next network is lead network. The lead network will act as a high pass filter. Now this is the lead. Lead network will act as a high pass filter. Now the combination of lag lead compensator. Now the combination of lag lead compensator. The combination of lag lead compensator will act as a band stop filter. Therefore, here is also you can observe the lag will occur at low frequencies, lead will occur at high frequencies. Therefore, the lag lead compensator will act as a band stop filter. If it is a band stop filter, the pole 0 sequence in S-plane is pole 0 0 pole. Clear or not? No doubt. Okay. Now this is the compensators and the combinations of the compensator. Not only that, and also you observe now what should be the pole 0 sequence in any filter. So if any electrical circuit is given, first to simplify those circuits, locate the poles and zeros on S-plane. If those poles and zeros located on S-plane and based on the location of poles and zeros, then you decided which type of filter it is. Now see here. Now this is magnitude or a gain. Now this magnitude or gain which is equal to 1, which is constant, which is equal to 1 and which is independent of all the frequencies. Now see here, this gain which is equal to 1, this is the gain which is equal to 1 for all the frequencies, means it will allow all frequencies, because for all the frequencies the gain is multiplied with 1. Generally pass band means gain is multiplied with 1, stop band means gain is multiplied with 0. But for all the frequencies the gain is multiplied with 1 means all frequencies are allowed, right? Then no frequency is attenuated, all frequencies are allowed. Therefore this is called as all pass characteristics, all pass filter characteristics. Means now how this filter characteristics means, now all pass system, how it looks like. Now what are the post zero sequence in a all pass system? Now we will try to explain. Okay. Now let us see here, if your transfer function is like this, 1 minus st by 1 plus st. Let's find gain or magnitude, okay, which is equal to 1 minus j omega t by 1 plus j omega t. What is the magnitude? Square root of a square plus b square, square root of a square plus b square, which is equal to, this is the magnitude, which is equal to 1, which is constant and which is independent of all the frequencies. The magnitude gain which is equal to constant and which is equal to 1 for all the frequencies. Now it will produce all pass filter characteristics, means what is the pole zero sequence in S plane? Now 1 0 is at plus 1 by t, then there exists a pole at minus 1 by t, which means that there exists a symmetrical pole zero location. There exists a symmetrical pole zero location. Now this is the symmetrical arrangement, means if the poles and zeros are arranged symmetrical in the S plane, now that particular symmetrical pole zero location is producing a all pass filter characteristic, and that particular system is called as all pass system. Now for example, this is the origin, 1 0 is at plus 1, 1 0 is at plus 2, 1 0 is at plus 3. If this system is to produce an all pass system characteristics, then there exists a symmetrical pole at minus 1, at minus 2, at minus 3. Now this is the symmetrical arrangement between the poles and zeros with respect to origin or with respect to imaginary axis. Then that particular system is called as all pass system or all pass filter characteristics. Now there exists a complex conjugate poles. Then there exists a complex conjugate zeros on the right hand side of S plane. Symmetrical poles and zeros are location in S plane, then this is all pass. This is all pass. This is all pass. Symmetrical pole zero location in S plane, and it is said to be a all pass system or all pass characteristics. Okay, note down.